Okay, 9 a.m. Good morning, everyone. And we can continue. What? 2 weeks only left to the end of the semester. Not much. Okay. Anyway, so in the previous lecture, which we had just before Thanksgiving, finally we wrote down all Maxwell's equations. Right. So there are 4 of them. 2 allows us to find electric field, and 2 equations allows us to find magnetic field, right? And then we also added additional equation, equation number 5, which describes how those fields, electric and magnetic, interacts with a charge, right? So we added the Lorentz force, which consists of 2 forces, electric force and magnetic force. So that set of equations, 5 equations, right, forms the foundation of electromagnetism. So basically it means that any electromagnetic phenomena we should be able to describe using those 5 equations. So far no one could find any phenomena which couldn't be explained using those 5 equations. Of course, in the world of classical physics, quantum mechanical world, it's a different. Right. Okay, so now, so at that point, when Maxwell wrote down all those equations, right? So of course he started playing with them, right? Started playing, applying them. So and so he applied for the case when there are no charges in the space, there are no currents, right? And where is my key here? And just a second. Okay, no, still now. And so he, since there are 2 equations for the electric field, right? So he applied those conditions, no charges, no currents, right? And he combined those 2 equations, which allows us to find electric field. And he ended up with the equation like this. Second order partial differential equation. Some of you already took the course about how to solve equations like this. Some of you will definitely take it at some point at school, right? Because these equations are very, very important to describe some processes in the world, right? In the world of physics. Right. So he ended up with this equation. So we have what? Electric field in the y direction. So here the second derivative with respect to x, and here we have second derivative with respect to time, and some constant in front. Okay, cool. All right. So then there are 2 equations for the magnetic field. Again, he combined them, and he ended up with the equation like this. Right. Okay. Of course, this can be derived. And book, actually, the book, our book, goes through this derivation as any other book, as many other books. I did it only once. When I started teaching this course in 2014, I went through the derivation of these equations, right? And students sitting and looking at me with round eyes. What, are you crazy? Maybe I was, maybe I still am, right? But anyway, since that point, I decided, okay, I'm not going to derive this equation from the Maxwell's equations, right? So now I decided, so I will just present them without derivation. Okay, so if you combine 2 equations for the magnetic field, you ended up, or he ended up, Maxwell ended up with this second order, again, partial differential equation, right? Okay, back then, the researchers already knew this type of equations. They were well familiar with these equations. They knew that solutions of these equations are traveling waves. Okay, I need to mute somebody. Okay, so they knew that these are wave equations, and solutions, their solutions are traveling wave equations, which we discussed in our previous recitation class. Some of you will discuss it today, right? But again, I ask you to watch the video, right? Okay, and he also knew that these factors in front of this time derivative, this factor and that factor, it's a square of the speed. So we have this traveling wave, this traveling wave. So of course they travel, of course they have some speed. And factor in front of this time derivative, it's a square of the speed. Okay, I need to again press on the slides. Okay, so this square of the speed. Okay, and you see the square of the speed depends on our innocent universal constant, permeability and permittivity of, all right? Okay, so it looks like we're going to get some constant. So he calculated speed as 1 over square root of mu naught epsilon naught, because we know those constants and he knew those constants, and he ended up with this number. And that probably was quite shocking for him, because, okay, he ended up with 3 times 10 to the power of 8 meters per second. Also, people back then already, researchers back then, at the end of 19th century, they already managed to measure the speed of light. So he knew that this is the speed of light. And can you imagine that after he came up with this conclusion, basically it's a realization that light is electromagnetic wave. It was quite a shocking, it should have been, it was a, I guess, am I guessing, right? It was a quite a shocking conclusion for him. If he had a weak heart, he would probably have a heart attack, right? Because he was the first person in the world who realized that light is an electromagnetic wave. And it was obvious proof, right? Okay, yeah, it means that light is electromagnetic wave. Yeah, that was quite a shocking conclusion for him, right? So now, after this, right, so let's discuss solutions of these 2 second-order partial differential equations. Again, he knew the solutions, and you will learn how to solve these differential equations. Right? When I took this course, I remember I liked those. Okay, so anyway, solution of this equation will be the well-known for us now. Oops. Okay, sorry, I pressed too hard my clicker. Right. Solution of the first equation, it will be a traveling wave equation. And now you see why I digressed and to chapter 16, and we spent almost the whole recitation class, and I asked you to watch a video to be familiar with this, with the traveling wave equations, because solutions of this is a traveling wave equation. So electric field oscillates in the y direction. You see E sub y, so it means that the electric field oscillates in the y direction, but the wave propagates in the x direction. An example of a transverse wave. Electric field oscillates perpendicular to the direction of wave propagation, right? Okay, then solution of this, very similar, but now, of course, for the magnetic field, and of course, you see magnetic field now oscillates in a z direction, perpendicular to the electric field, and still propagates in the x direction. So we have basically 2 traveling waves propagating in the same direction, in the x direction, in the positive x direction. And electric field oscillates in the y direction, and magnetic field in the z direction. Okay, so now we know how to analyze these traveling waves. We know how to get wavelength, frequency, the speed. We're familiar with these equations, right? Okay, so now let me just again remind you. Right, so of course, these are amplitudes, electric field amplitude and magnetic field amplitude, right? Then K is a wave number, spatial frequency, basically. Again, we're going to use this term, spatial quantity, temporal quantity, right? Again, K, it's a spatial frequency called wave number, and it is introduced as 2 pi divided by lambda. Lambda, it's a spatial periodicity of the wave in space. Then omega, angular frequency, right? Again, the meaning, it's basically temporal frequency. And it was introduced in a similar way like this K. So omega, but now it's a 2 pi over T, because this angular frequency, it's a temporal quantity. So we introduce it as 2 pi divided by temporal periodicity of the wave in time. Okay, then, of course, minus means that this particular wave propagates in the positive x direction, right? If we had here plus, it would mean that the wave propagated in the negative x direction, right? If we had here, let's say z over here, z, it would mean that the wave propagated in the z direction. Right? Okay, then what's next? Of course, this is electromagnetic wave, and as we just saw, it propagates with the speed of light, right? And of course, yes, still we can find that speed as the ratio of this temporal quantity omega versus this spatial quantity wave number. Again, I discussed it in the video and we practiced it in our recitation classes, right? Or you can do it also, calculate this v, which is c, speed of light, this speed of light, right, as lambda f, right? Lambda wavelengths times the frequency of the wave. Then these amplitudes, electric field amplitude and magnetic field amplitude in the electromagnetic wave, they are not independent. They depend on each other. And the electric field amplitude equals magnetic field amplitude times speed of light. So you see electric field amplitude is way larger than amplitude of the magnetic field. The coefficient of proportionality is speed of light. Speed of light is a gigantic number, right? Okay, so if amplitudes of the electric field and magnetic field in the electromagnetic electromagnetic wave, they're dependent, right, to the speed of light. So if you know, for example, magnetic field amplitude, you should be able to find electric field amplitude, piece of cake. Again, this can be shown during this derivation of these equations, right? Again, I've done it, but as I told you, I decided that it's not worth of quite a rigorous calculus, maybe like half an hour of rigorous derivations. Decided it's not worth of doing this, right? But again, it can be shown. And so this construction is called electromagnetic wave. Okay, and now let's look at the picture of electromagnetic wave. Okay, just a bunch of framing, and now the picture. So first of all, let's start with the coordinate system. You see we have x direction, it's that way, y direction straight up, and z direction is out of the screen, out of the board. Right? And you see we have electromagnetic wave, so yeah, it propagates along the x direction, so direction of the speed is that way. Electric field, as we saw on the previous slide, oscillates in the y direction. You see y direction is vertical, so first amplitude, electric field, electric field becomes first stronger, then it gets 0, then it becomes negative, then again goes up and down. So you see it's a electric field traveling wave, which propagates this way. And next to that one, there is a traveling wave, magnetic field traveling wave. Magnetic field oscillates in the z direction, you see, first in the positive z direction, then goes to 0, then negative z direction, then again positive z direction, negative z direction. And they propagate together, oscillate and propagate together. Then, basically, it's a... you remember at the end of the video, which I asked you to watch, I discussed two types of graphs which can be used to analyze traveling wave. You remember history graph and snapshot graph. What is this? It's obviously a snapshot graph. If we could take a picture of the wave, we would be able to get something like this. You know what? Once I said that, I'm not completely sure, because that's how we model the electromagnetic wave. If we had a chance to take a picture of the wave, who knows what we would be able to see, right? Because that's how we model it, right? It's our way of modeling, and it works, and that's why we use it, right? But anyway, so according to our model, that's electromagnetic wave, right? And it's basically it's a snapshot graph. So it's basically a picture of the electromagnetic wave at a certain moment of time. Time is frozen in this picture, right? So it's a snapshot graph. And you remember, in a snapshot graph, time information pretty much is missing. We just know maybe this was taken at 5 seconds after initial moment of time, for example, right? But we see plenty of spatial information. And of course, the distance between this peak and this peak will be wavelength, right? Or between this peak and that peak, wavelength. So between this blue peak and that one is the wavelength, right? The wavelengths you can see over here. Then, of course, every time, if it is an electromagnetic wave, these three directions, direction of the electric field, direction of the magnetic field, and direction of propagation, they must be mutually perpendicular to each other. If they are not perpendicular, there must be something wrong in your descriptions, right? All the time, they are perpendicular to each other. All right. Okay, then, next, interesting feature of an electromagnetic wave. Let's, for example, okay, I put this graphic here on purpose. So imagine yourself, for example, sitting here at this point and electromagnetic wave passing you by. So you're sitting here, and first let's look at what happens to the electric field. So you sit and you see electric field first. You see first it was at this point small, then it will get larger, stronger and stronger and stronger up to this point, and then it becomes weaker. And you sit, and all these electric fields are passing you by, right? So you see electric field changes in time. As you sit and observe electric field, it changes in time. You remember a couple of classes ago, changing in time, electric field, what does it produce? What does electric field produce, right? Magnetic field. Right? You remember we spent almost the whole class modifying Ampere's law, and we ended up with Ampere-Maxwell's law, right? And that additional term, displacement current, which basically describes production of the magnetic field by changing in time electric field. And that's what we have here. If you sit here and look at the electric field changes in time, so it means that there must be magnetic field produced. Which magnetic field? This blue magnetic field. This magnetic field is produced by the electric field. Wow. Now let's look at the magnetic field. You still sit at the same point, right? And observe now this blue, this magnetic field. Again, you see, if you sit here, of course, magnetic field passing through you first increases, then of course it will be decreasing, but anyway, it changes in time. And you remember Faraday's law. It tells us that if you have magnetic field changing in time, it will produce magnetic field, or electric field. It will produce electric field. This electric field, oh my God, so these two fields, electric and magnetic field, produces each other. So first, electric field produces magnetic field, and at the same time, changing in time, magnetic field produces electric field. It's the most amazing system. It's the most self-supporting system, self-sustainable system. So electric field produces magnetic field produces electric field, and they happily propagate through space. It's the most self-supporting system, self-sustainable system. And they can propagate forever if there are no any absorptions. And that's why our universe is filled with microwave radiation, basically electromagnetic waves traveling through the universe since the Big Bang. Because yeah, they can easily propagate almost forever. I produce you, you produce me, and we happily travel through space. It's the most amazing system. Then, what else? The electric field reaches maximum at the same moment and at the same point as magnetic field. They reaches zero at the same point. They reaches minimum at the same point. Basically, these couple, electric field and the magnetic field, they share ups and downs. They regenerate each other. It's the example of, I don't know, eternal true love. the most self-supporting system, self-sustainable system, the happiest couple, right? And yeah, for me, it's probably the most amazing system, right? And they will never split up. They all the time travel together. It's not like in our life, you're not making me laugh anymore, I'm leaving you, right? Okay, this is, again, in my opinion, the most amazing system, electromagnetic wave, right? Okay, so now after discussing this, right, so now next. And of course, Maxwell, when he realized that light is electromagnetic wave, he also came up with the conclusion conclusion that electromagnetic wave can exist at different frequencies. And he realized that there's the whole spectrum, electromagnetic spectrum. On one side of electromagnetic spectrum, we have radio waves, and on the other side, we have gamma rays. Of course, so we have radio waves, then microwaves, then terahertz, then infrared, then visible, then ultraviolet, then X-rays and gamma rays. These are all electromagnetic waves. They all travel with the speed of light. If problem says that there is a radio wave, it should immediately tell you that it travels with the speed of light. Of course, the problem is not going to tell you, guys. Remember, it travels with the speed of light. No, you should be able to realize that. Right? But of course, frequency and the wavelengths are going to be different. On this side, radio waves, radio signal, they have large wavelength, but small frequency. The wavelength can be meters or maybe even kilometers, right? A large wavelength, small frequency. But if you multiply lambda f, you will get speed of light. But if you go to this side of the spectrum, gamma rays, so the wavelengths will be teeny tiny, but the frequency will be very, very large. And again, if you multiply lambda times f, you will end up with the speed of light. Okay, so electromagnetic spectrum. And now after this, I think it's time for me to look at the example, right? Example of playing with calculating parameters about, or parameters or quantities of electromagnetic wave. Okay, so let me switch to the whiteboard. So it's a problem 3115. We're not going to discuss these problems in our recitation class. So we just look at this example and it should be enough. So we have electromagnetic wave propagating in a vacuum. And what is given, basically it's a traveling wave, electric field traveling wave. E sub y, then amplitude 20 volts per meter, and then cosine 6.28 times 10 to the power of 8 x and minus omega t. And we need to find a bunch of parameters. Okay, I'll grab my notes. So what needs to be found? So first of all, let's discuss a few things. First of all, cosine function, because in the video which I asked you to watch, I used sine function. And some students panic when they see cosine function. What should we do, right? Okay, there's no point for panicking, because what's the difference between sine and cosine function? The phase of pi over 2. If you shift, for example, sine function by pi over 2, you will get cosine function. So we can get this, for example, easily out of sine function, which I used in the video. So for example, okay, let me write first y. Okay, it doesn't look like y. Let me change it. Y cosine function. Okay, so let me show that if you, okay, let me write E naught. Okay, let me use sine function, kx minus omega t plus phi naught. So that's what we had in that video, that's what I had in my video, right? So if phi naught equals to initial phase equals to pi over 2, then you remember trig identities from high school. This gives us cosine function. So you'll get E naught cosine of kx minus omega t. And that's what is given, right? So it's just that equation which I used. In that equation which I used, initial phase is pi over 2. So there's no point of panicking. Then, now let me plot the graph, right? It's a snapshot graph, again, like what we had just now in my presentation. So electric field oscillates in the y direction. So here I drew coordinate system. So electric field oscillates in the y direction, in the vertical direction. But the wave propagates along x-axis that way. And actually, since we have minus, it means it propagates, this traveling wave propagates in the positive x direction. So I can draw electric field, traveling wave. So it's a cosine function. So let me start it like this. Right, so this will be electric field. Right, so that's E. Right, and it travels that way. Then you remember that these three directions, direction of the electric field, magnetic field, and direction of propagation must be perpendicular. Since the direction of propagation is that way, so it travels, wave travels that way. So for the magnetic field, there is only one direction left, z direction, right? Because E along y, x, it's a direction of propagation, so there is only one direction left for the magnetic field. So magnetic field oscillates along z axis, right? And let me draw something like this, right? So magnetic field in the horizontal direction, z direction. Okay, so now let me draw also magnetic field vectors. So that's B. Right. So, and again, you see, they oscillate in unison. So they share ups and downs. They reach maximum at the same time, zero at the same time, minimum at the same time. So it means what? It means that everything that we have in a cosine or sine function is exactly the same for both magnetic field and electric field. The only difference in the directions and amplitudes. This structure, x and time dependence, are exactly the same for both electric fields and magnetic fields. All right? In the electromagnetic wave, of course, only in the electromagnetic wave. Right, so let me check if I mentioned everything. Yeah, okay, now after this, let's find what problem ask us to find. Then, before I go, quite often I give something like this on the final exam. And if wave propagates, let's say if wave propagates in a z direction, over here we would have z. If wave propagates in a y direction, over here we will have y, right? And then x, direction of x and direction of E and direction of B must be, okay, the problem will say about something, some direction, right? And then, of course, you should be able to come up with a conclusion about direction of some, for example, magnetic field. But again, remember, this is direction or axis along which wave propagates. Okay, so now let's answer actually questions. Part A, we need to find what? Wavelength. We need to find wavelength. Wavelength, it's a spatial periodicity. It's a spatial quantity describing traveling wave. Right, so all spatial information about the wave is hidden in this term, kx. Right, everything about all spatial parameters we should be able to find from here. Okay, yeah, and so k is given, wave number. Right, so let me write k equals 2 pi over lambda. And from here, of course, we can find lambda. It will be 2 pi over k, and this is k. Maybe I should frame it and emphasize that this is, of course, k, wave number. All right. Okay, so 2 pi, it's 6.28 divided by 6.28 times 10 to the power of 8, right? So these units of wave number, it's m meters to the power of -1. So it means meters go upstairs in the numerator. 6.28 will disappear, and we will get wavelengths 1 times 10 to the power of -8 meters. Right? Yeah. Okay, so wavelength. Then next, what's next? A frequency, B. Let's find frequency. Just a normal frequency, not angular frequency, F. So F, frequency, again, it's a temporal parameter. So, and now it looks like we're in troubles. Because again, you remember where is all temporal where the temporal information is hidden? In this, right? Omega t. It has all temporal information. And omega is not given. Omega is not given in the problem. Right? Of course, we would usually use this, right? So omega is introduced as 2 pi over t, or 2 pi f, and from here, if omega were given, of course, we would be able to find f. But omega is not given. But omega is not given. Big sad face. So it means what can be done in order to find anything, in order to find, okay, that temporal quantity frequency. Because again, omega is missing. Okay, now we need to realize that this is an electromagnetic wave. And we know additional piece of information about electromagnetic wave. We know that it travels with the speed of light. We know the speed. And you remember in our recitation classes and in the video which I asked you to watch, I told you that speed, it's neither spatial nor temporal quantity. It's sort of like a mix. It works as a bridge between temporal quantities and spatial quantities. And speed is given. So speed should allow us to find f. Otherwise, if it wasn't an electromagnetic wave, yeah, we wouldn't be able to solve this problem. Right? Okay, so, but we know that V equals C, and of course 3 times 10 to the power of 8 meters per second. Right? Okay, so now which formula is better to use? I think it's better to use V equals lambda times f, because we just found lambda. V, it's the speed of light, and so we can find f. So from here, we can get that f equals to c over lambda. Okay, I changed V to c immediately, right? Okay, so c, 3 times 10 to the power of 8 meters per second divided wavelengths are these. You know what, let me underline these wavelengths. All right, so 1 times 10 to the power of 8 meters. Okay, so we're getting 3. Oh, it's such a nice number. 3 hertz? Really? Minus 8. Because I'm looking at some, it looks weird. No. Okay, I need to look carefully. 1 times 10 to the power of minus 8. Because that's too, frequency is too small. It cannot be true. Right, so 10 to the power of minus 8 goes upstairs with positive power, so it will be 3 times 10 to the power of 16 hertz. Okay, yes, this sounds correct. Let me check. Yeah, of course. So now we found the frequency. Okay, let me also underline it so that it will be easier for me to find then later. Okay, so now since omega is not given, so let's find omega. Because at the end I want to write traveling wave equation for the magnetic field. So, and we will need omega. So since we found F, so we can find omega using this. Right? So now omega equals 2 pi F, right? So it will be 6 pi times 10 to the power of 16 radians per second. So omega. So now we can actually correct expression for the electric field. So now omega, we know omega. So what's next? Magnetic field amplitude. Because again, at the end, I want to write the traveling wave equation for the magnetic field. Right? So now A, B, C, now C. Magnetic field amplitude, B naught. And again, you remember, a couple of slides ago, I told you that amplitudes of magnetic field and the electric field in the electromagnetic wave, they are connected through the speed of light. And electric field is way, way, way stronger by a factor of c, speed of light. So we can find then easily B naught equals to E sub 0 divided by C. Again, speed of light. Very often on the exam, students, I don't know, for whatever reasons, they don't remember that, or maybe they just don't come to classes, right? So E naught amplitude is given, so it will be 20 volts per meter divided by speed of light, of course, 3 times 10 to the power of 8 meters per second. Right? So if you take a ratio, it will be 6.666, right? 6.67, okay, let me write approximately, times 10 to the power of minus 8 Tesla. Right. Okay, so now we know amplitude of the magnetic field, and now after this point, we should be able to write the expression for the magnetic field. Right. So magnetic field now, I think it's a part D. Yeah. Right. So what? B. Sort of. I want to write similar, but now for the magnetic field. So electric field oscillates in the y direction, direction of propagation x. Magnetic field oscillates in the z direction. So we need to put a subscript z, which is the function, of course, of x and t, because this traveling wave, magnetic field traveling wave, also propagates along x direction, right? So it depends on x and time. So now B naught, this, right? So 6.67 times 10 to the power of minus 8 Tesla. Then, and after this, x and time dependence are exactly the same for as the x and y, x and t dependence of the electric field. So just rewrite this, and of course now we know omega. Right. So it will be cosine k. Okay, it looks like I'm running out of space. 6.28 times 10 to the power of 8 x. Oh, maybe I can continue on that side of the board, whiteboard. Minus omega. Omega is here. Right. So it will be minus 6 pi times 10 to the power of 16 times t. Right. So expression for the traveling magnetic field traveling wave, right? So again, where are the typical mistakes? Direction of propagation. Then correct subscripts. Remember, all these three directions must be mutually perpendicular. And this is an example of a transverse wave. Electric field oscillates perpendicular to the direction of propagation. Magnetic field oscillates perpendicular to the direction of propagation. So all the time, this direction, in this case x, and that direction y must be perpendicular. Then of course here the same. This and that must be perpendicular. Right? These are typical places for mistakes on the exam. Okay, so yeah, after this you should be able to solve problems like this, right? Again, as I said, from time to time I give problems like this on the final exam. Okay, if you have questions, ask. All right, so we still have 7 minutes. So let me switch back to the presentation. So now, what's next? Couple of questions. So, old days radio receiver. Okay, just a radio. It has an antenna like this. You see just a piece of metal rod. Right. It can be positioned horizontally, vertically, right, or at the angle. It's up to you. So let's assume that a radio wave is generated by a radio transmitter antenna. Basically, and you see it's written straight metal rod, which is vertically positioned. Right. And it generates this electromagnetic wave. Electric field, you see, oscillates in the vertical direction. Magnetic field oscillates in the horizontal direction. Sorry. All right. So now, how should we orient antenna of this radio in order to get healthy reception? Should we orient it vertically or horizontally? Or maybe at some other angle. Okay, so the answer is more or less obvious, right? The poll is in the chat. I can see it. You should be able to see it also, right? So, can you? Okay, I see you already started answering it, right? The answer is more or less obvious, right, for most of you, but I want to discuss the reason. Okay, I see. Okay, interesting distribution of answers. I'm just looking at numbers. Okay, we'll have almost like 50-50. Some people believe it's answer A, some people believe it's answer B. Okay, okay. Very close. Too close to call. All right. Wow. 46-46. Okay, guys. Yeah, I need to start discussing, right? Before the end of the class. Before the class ends. Okay, I see that. I expected that will be a different distribution. Okay, anyway. So, so this is our electromagnetic wave produced by the antenna of the transmitter. Basically, antenna which generates electromagnetic wave. Electric field oscillates vertically. And now let's discuss both orientations. First, let's position our antenna of our receiver, antenna of this radio. Let's first position it vertically. Oh, right. So let me press on slides. Position it vertically like this. So you see. So in this case, of course, antenna is just basically piece of metal, right? And you remember properties of a metal, it has tons of free electrons. When they feel electric field, of course, they will start running, right? Okay, so these electrons, they feel this electric field, and the electric field oscillates in the vertical direction, up and down, up and down. Of course, these electrons will start feeling electric force, Q times E, right? And of course, they will start oscillating also up and down with the electric field. Electrons, of course, in the opposite direction because they are negatively charged. But anyway, they will be also oscillating up and down, up and down. And now they have plenty of space, plenty of room in this direction, so they can go up and they can go down, generating a reasonable amount of current in this antenna. And that current can be coupled out to the, for example, to the radio, and then something can be done to that signal to produce, I don't know, signal, right? So in this case, yeah, we will get reasonably healthy current. But now let's position our antenna horizontally, like this. So antenna now position is horizontally. Of course, again, it's still the same antenna, still has tons of free electrons, and of course, those electrons, like electrons here, they, of course, they feel electric field, and of course, they will start running, right? They will start running, but now, once they try to move up following the electric field, very soon, they will hit the ceiling of the antenna, because here, the edge of the antenna. So they will hit the ceiling without being able to move significantly. Okay, maybe bad luck. So they turn around, and with the next cycle of the electric field, they will go in the opposite direction, down. And the same, again, they will hit this bottom very, very soon. So basically, they want to run like in this case. But now with this orientation, electrons just don't have space to move. Just a second. They don't have space to move. Here they hit the ceiling, here they hit the bottom, right? So they try to run, try to generate current, but they just don't have space to do that. As a result, here, current will be minuscule on the level of noise, and you will you cannot generate current, and as a result, you cannot get the signal from the electromagnetic wave. Of course, in this case, you will get nothing in your radio. So the antenna, this antenna, straight rod, like over here I have, where is my antenna? Here, right? You see, typical antenna. So these two rods are designed to pick information from the electric field. And of course, in this case, if electric field oscillates vertically, so in this case, I will be able to get healthy signal. If I position my antenna like this, I wouldn't be able to get significant amount of, I will get the signal on the level of noise, right, from the electric field. Okay, so most likely we will continue next class. Maybe I will spend 5 minutes discussing this. And next, click a question. Okay, so the answer is A, vertical. Right. Okay, so now after discussing the logic, you will never pick option B, right, for the questions like this, for the question like this. Okay, guys, sorry for holding you. Okay, extra minute, but it's not a big deal. Okay, guys, so if you have questions, ask. If not, I will see some of you tomorrow and some of you on Thursday. In our next recitation class on Wednesday and Thursday, we're going to start introducing interference. We're not going to discuss that in our lecture. We're going to do that in our recitation class, so don't miss that. Okay, guys.